Hello, myself Prashant Kumar Srivastav. I am physics teacher. Today I will teach about the stationary waves. Stationary waves are produced by superposition of two progressive waves of equal amplitude and frequency traveling with the same speed in opposite direction. Okay, this is about the stationary waves, and this is the given diagram about the stationary waves. There are two different progressive waves are superimposed to each other at the different points. Where there is displacement is maximum, that is called antinodes, and where there is a displacement is zero, that is called nodes. Production of stationary waves. This is the method of the production of the stationary waves. There are the vibration generator. Due to the vibration generator, we are producing the frequency, and this due to this frequency, strings are vibrated, which is connected with the stand, and there is stationary waves is produced in the string due to this vibration generator. Properties of stationary waves. Stationary waves have nodes when where there is no displacement at any time. In between the nodes are position called antinodes, where the displacement has maximum amplitude. This is the diagram of the stationary waves. Okay, this is the diagram of the stationary waves. Now next is the properties of a stationary wave. There is nodes. Stationary waves are travel in the form of nodes and antinodes. All particles between two adjacent nodes are in phase. There are two type of stationary waves. One is the transverse stationary waves and another is the longitudinal stationary waves. Transverse stationary waves in the string and longitudinal stationary waves in the sound. And this is the formula in the case of when strings are connected at both the points. This is the method for calculating the frequency. Standing waves in a string fixed at both the ends. F1 is called the fundamental frequency. The higher frequency are integer multiple of the fundamental frequency. These normal modes are called harmonics. F1 is the first harmonic, F2 is the second harmonic, and so on. Modes of the vibration of string. There are three different modes which are more important. First is the fundamental node, second is the first overtone, and third is the second overtone. In the fundamental notes, there are one antinodes and two nodes. And in the first overtone, there is two antinodes and three nodes. And in the second overtone, there is the four nodes and three antinodes. Investigating stationary waves using sound waves and microwaves. Moving the detector along the line between the wave source and the reflector enables alternating point of high and low signal intensity to be found. These are the antinodes and nodes of the stationary waves. The distance between successive nodes or antinodes can be measured and correspond to half the wavelength lambda. If the frequency f of the source is known, the speed of the two progressive waves which produce the stationary waves can be obtained. Okay. Resonant frequency of a vibrating string. Resonant frequency means that if the natural frequency of body is same as the given frequency, then the vibration of body increases, that is called resonant frequency. From the experiment we find that there is number of resonant frequency in a vibrating string. The lowest resonant frequency is called the fundamental frequency. The other frequency are called overtones. Each of the overtones has a frequency which is a whole number multiple of the frequency of the fundamental. Factors that determine the fundamental frequency of a vibrating string. F is equal to 1 upon 2L root T upon mu. Mu means mass per unit length, T means tension, and L means length of the string. This is the formula for the fundamental frequency of stationary waves. Vibration in air column. When a loudspeaker producing sound is placed near the end of a hollow tube, the tube resonates with sound at certain frequencies. Stationary waves are set up inside the tube because of the superposition of the incident wave and the reflected wave traveling in opposite directions. Factors that determine the fundamental frequency of a vibrating air column. The natural frequency of a wind instrument is dependent upon first, the type of the air column, second, the length of the air column of the instrument. There are two different type of organ tube. First is the open tube and second is the closed tube. In open tube, length is lambda by 2 and in the closed tube, length is lambda by 4. Standing waves in a string. This is the fundamental notes. This is the diagram of the fundamental notes. And another one is second harmonic and the third is the third harmonic, which is already discussed. This is the diagram of the open organ pipe where fundamental notes and first harmonic and the second harmonic. Modes of vibration of an open tube. This is the diagram of an open tube. Fundamental notes, first overtone and second overtone. And this is mode of vibration of a closed tube. For fundamental, frequency is V upon 4L. For first overtone, frequency is 3V upon 4L. And for a second overtone, frequency is 5V upon 4L. The quality of sound. This is the quality of sound for given second overtone, fundamental and first overtone. This is the Chaldean's plate. Chaldean's plate is an example of resonance in a plate. Resonance, all elastic objects have natural frequency of vibration that are determined by the material they are made of and their shapes. Okay, and this is the tuning fork. By the help of tuning fork, we are produce the frequency which is same as the natural frequency of given body. Okay, thank you. And next I will discuss derive the different fundamental notes. Then from principle of superposition we know that y is equal to y1 plus y2. Y is equal to y1 plus y2. And both are the progressive waves, and for a given progressive waves y1 is equal to a sine omega t plus kx and y2 is equal to a sine omega t minus kx. We are putting the y1 and y2, then we are getting y is equal to a sine omega t plus kx plus a sine omega t minus kx. A is common, then y is equal to a, and this is sine omega t plus kx, sine omega t plus kx plus sine omega t minus kx. We are using the formula of trigonometry. This is sine c plus sine d, sine c plus sine d, and this is equal to 2 sine c plus d upon 2 into cos c minus d upon 2. Then we are getting y is equal to 2a sine omega t plus kx plus omega t minus kx upon 2 into cos omega t plus kx minus omega t minus kx and upon 2. After solving, we are getting plus kx minus kx cancel, omega t cancelled. Then y is equal to 2a sine omega t into cos kx. And this is the equation of stationary waves. This is the standard equation of stationary waves. Now if we want to calculate the frequency, suppose we consider point x is equal to L. At point x is equal to L, at point x is equal to L, y is equal to 0. Then we are putting the value. Therefore 0 is equal to cos k into L. Then cos k into L is equal to cos pi by 2. Then this cos k into L is equal to cos 2 and pi minus pi by 2. Then k into L is equal to 4n minus 1 into pi by 2. Putting the value of k is the propagation constant, and we all know that k is equal to 2 pi upon lambda. K is equal to 2 pi upon lambda. Therefore 2 pi upon lambda into L, and this is equal to 4n minus 1 into pi by 2. Pi is cancelled out, and therefore lambda is equal to 4l upon 2n minus 1. And we know that since frequency is equal to v upon lambda, then therefore frequency is equal to v into 2n minus 1 upon 4l, and this is the frequency. This is the frequency of a stationary waves. Okay, thank you so much.